So first of all, I would like to thank organizers of the conference for giving me opportunity to present my results. And I apologize that I could not participate in the conference in person due to personal reasons. So I have to make the talk remotely. I am experimentalist and present here to organizations, Moscow Institute of Electronics and Mathematics of HCE University. And my laboratory is in Kapitsa Institute, also in Moscow, in Russia. My collaborators are Jan Lehtinen, who is also experimentalist from Finland, and theoretical support is made by guys from Moscow and Germany, Andrei Zaikin, Andrei Semenov, and Alexei Ratkevich. So what the story is about? Actually, as I understood, I have 20 minutes for my talk, and I'm planning to speak actually quite a lot. So I will go quite fast. I hope in first 5 minutes, I will make a brief introduction about what are the fluctuations of the order parameter and what is the concept of quantum phase sleep. Next 5 minutes, I will spend for relatively old results, our own results showing integral properties and how they are affected due to quantum phase sleep effects. And the last 10 minutes, I will spend mainly for the new results, which are not yet well advertised. So what the story is about, I'm going to speak about quasi-one-dimensional superconductors. The characteristic scale is the coherence length. So in our samples, it is something of the order of 100 nanometers. So modern nanotechnology is capable of fabricating nanowires with cross-section smaller than 100 nanometers, no problems, and they are sufficiently long. So the most famous property of superconductivity is the resistive transition, and it would be very convenient to make introduction to fluctuations of the order parameter in superconductors, speaking actually about resistivity. Let us consider that on this cartoon, everything which is in normal state is shown in red, and everything which is zero resistance in superconductor is green. So let us first concentrate on the top of the transition. So resistance versus temperature, and I'm speaking about the top part of the transition. And the answer is known. This is a contribution of Aslamazov-Larkin, which shows that for all dimensionalities 3, 2, and 1D, the impact of these fluctuations lead to rounding of the top part of the transition. So the corner here will be rounded. Now let us turn to the bottom part of that transition, where the system is mainly in superconducting state, but here and there that might appear some normal domains due to fluctuations. One should not be an expert in superconductivity to understand that in 3D and 2D, nothing interesting happens, because supercurrent prefers to go along the zero resistive part, the green one here. So whether we have these red spots or not doesn't matter. But situation is dramatically different if one speaks about one-dimensional case where a single fluctuating domain can block the supercurrent. So how it is assessed in theory? So let us suppose that we have a long superconducting wire with cross-section sigma smaller than the coherence length, so it is quasi-one-dimensional system. And theories say that there is always finite probability that here and there, instantly order parameter turns to 0 and phase changes by 2 pi. So there appeared such red spots. It's a dynamic process. So the minimum energy one should pay for destruction of superconductivity in such a point is the condensation energy, which is a very well known how to calculate from any textbooks in superconductivity. And if to consider that these events are quite rare, then the probability of such processes is exponential function depending on the energy spent to kill superconductivity within this red point, normalized by some energy. And the whole story is about what is in the denominator of this exponent. If we speak about the classical approach, then it is just thermal energy, kBT. and it is important, sufficiently close to critical temperature. There might be other situation, and that is the point of my talk, when the energy is the gap itself, so it's a quantum fluctuations of the energy gap. There is other approach, also cartoonish type. Let us consider that fluctuations happen in one particular point of the wire, let's say with some, where is some constriction. Then the free energy as a function of the order parameter is a well-known washboard potential. So if we have a classical process, then the whole system, represented here by a dot, can go over the barrier, and this will correspond to the classical case of thermal fluctuation. But as the system is quantum, it can also tunnel from one local minima to another, and this will be quantum fluctuation. Note that the initial and the final states are different in energy, in finite current, when the washboard potential is tilted, so it will lead to dissipation. So what are the manifestations? The very well-known manifestation, and that has been studied by us already more than a decade ago, and also other groups contributed, is the broadening of superconducting transition resistance versus temperature. Here are the plots from our old results. Left is shown for aluminum, right is shown for titanium. So the conclusion is that for sufficiently narrow wires, quantum fluctuations completely kill zero resistance state, and in the thinnest wire, the extrapolation of the dependence to absolute zero doesn't result in zero resistivity. Lately, for other materials already more complicated, niobium N, which is a very disordered superconductor, we also managed to show that in the thinnest wires, there is a contribution of quantum phase slips. So that was about the resistivity, effective resistivity of a superconductor, which is so-called integral property. You need a long, or let's say extended object to measure its resistivity. Other integral property, which also needs a finite dimension system, is persistent current, which happens, let's say, in superconducting rings. So how to measure persistent current in a tiny superconducting ring? It appears to be not an easy experimental task, but fortunately, we know that the system changes from one quantum state to another when the persistent current in the ring reach subcritical values. When the current in a system, in a superconducting system, reaches its subcritical value, it broadens density of state. So if to make tunnel spectroscopy of such a wire where there is a circulating current, we can, by probing tunneling through this ring, somehow recalculate it into persistent currents. And this task was made by us already 10 years ago, and we indeed showed that when the ring has sufficiently thick walls, everything goes according to classical textbook superconductivity, but when the cross-section of the wall starts to be sufficiently small, the periodicity changes strictly to one flux quanta, and the magnitude dramatically drops. And this is also the contribution of quantum phase slips. So to conclude this old part of my talk, one should say that the process, which is called quantum phase slips, leads to broadening of the resistance versus temperature transition and suppresses persistent current in nanorings. Both properties I call here integral properties, which need extended sample to be measured. But what about local properties? For example, like density of state or energy gap, which formally can be measured in a point, let's say by a tip of a tunnel microscope, or in our case, by a tiny NIS or SIS junction. For this purpose, we fabricated a structure which is shown here in the left plot, which has relatively massive aluminum wire, and across it there were several nanowires of different cross-sections. So the cross-sections of these titanium nanowires were selected like this, that in the thickest one we should not expect strong quantum fluctuations, but in the thinnest one, which exponentially depend on the cross-section of the wire, the probability of fluctuation, they should be very strong. And in this experimental configuration, we can measure both the integral property of each nanowire, let's say its resistance, or we can measure tunneling between such a nanowire and other massive aluminum electrode where no impact of fluctuations is expected. And here is the summary of experimental results. So for thick wires, we confirmed our old results that they show relatively sharp superconducting transition. For thin wires, the transition was extremely broad and the resistance was not extrapolated to zero. And when we measured the tunneling property, which characterizes the intersection point of the thick aluminum wire and thin titanium wire in the limit of quantum fluctuations, we observed more or less conventional IV characteristics. What I mean here by more or less, that they look very similar to BCS IV characteristics with relatively sharp horns, if to speak about the derivative as function of voltage bias, but they were sufficiently broadened into sub-gap region. And I will now speak about particularly why it happens. And additionally, if to zoom the IV characteristic at the origin at small biases, we observed also a Josephson current. So to conclude the bare experimental results, it appears that for the same nanowire, sufficiently thin, we observe that the resistance is not going to zero. The transition is very broad without reaching zero resistance state, but the local properties like density of state, energy gap, and Josephson currents, they more or less look like in a conventional superconductor. Why it's like this? To speak about the explanation or interpretation of our results, let us now come back again to the issue of fluctuations of the order parameter. So order parameter is, in a general case, a complex function which has its modulus and phase. So what I was speaking so far was so-called brutal fluctuations of phase slips, where at some moment of time, modulus of the order parameter goes to zero, and simultaneously the phase changes by 2 pi. So these are these abrupt changes of modulus and phase. But one should not forget that there exists also a weak fluctuation, so-called Gaussian fluctuations, both of the modulus and also of the phase. And the theories say that the fluctuations of the phase are responsible for generation of soft plasmonic mode, so-called Muishon mode, which propagate along the nanowire, cause redistribution of electronic states, which broadens the density of state of the superconductor and the energy H. So formally, this broadening of the density of states can be described by the famous Dyne's parameter, that now the density of states becomes a complex function, which is broadened. But here the origin is completely different. In original paper, Dyne's considered that this broadening happening due to finite lifetimes as quasi-particles. Here it's the result of quantum fluctuations, the Gaussian fluctuations of the phase. And our theories calculated that indeed the energy gap broadens sufficiently close to the energy gap. And here it is important to introduce 2 characteristic parameters. One parameter, so-called G with index psi, is responsible for dimensionless conductance, and it characterizes the fluctuations of the order parameter or also of the quantum phase slips. And it exponentially is in the rate of quantum fluctuations. Other dimensionless parameter, so-called admittance, accounts for the hydrodynamic or long wavelength interaction of fluctuations. And this parameter is responsible when we want to speak about interaction of phase slip events which happens due to propagation of these Muir-Schonn waves. And there is shown that the characteristic value of this admittance equal to 16 corresponds to superconductor insulator transition. And here they have introduced the characteristic length scales shown here at the bottom, which separates the system from being completely insulator from the condition when some superconducting properties might be manifested. So on this image, prepared by my co-author, Andrei Semyonov, naively one can understand what I'm going to speak about. So the quantum phase slip is the tunneling of the flux quantum through a superconducting nanowire. So this characteristic length scale, x with index c, is the threshold. If the system is sufficiently long, then on these scales, quantum fluctuations completely wash out their superconducting correlations. So on the long scales, the measured integral properties are losing their superconducting properties, like I have shown in the first part of my talk. No zero resistance state, no persistent current. But if system is smaller than these characteristic length scales, then superconducting correlations are not washed out completely, and measuring these properties on a shorter scales, like made in this experiment, for example, measuring tonal characteristic, we can detect something which resembles conventional superconductivity. Indeed, so for the same structures I shown you before, the theory fits show that the shape of the resistance versus temperature transitions can be nicely fit by the model of quantum phase slips for different wires. But because the probability of quantum phase slips exponentially depends on the cross-section of the wire, for thicker samples, it's relatively abrupt superconducting transition, but for thinner wires, it is not. But all of these transitions can be nicely explained by the mode. When now we speak about the local properties, here is a family of IV, actually the derivative di dv as function of voltage for the same wire at different temperatures. They are all normalized to be here equal to 1. Again, theory manages to fit to the experimental dependencies. And the broadening I spoke about from the theory point of view, indeed is observed in experiment, and it nicely corresponds to theory prediction. So my conclusions. So quantum fluctuations of the order parameter is a universal phenomena which has impact on both integral and local characteristic, if to speak about quasi-one-dimensional superconductor. In sufficiently thin nanowires, a finite electrical resistance can be observed at the lowest temperatures, which is explained in terms of localization of Cooper pairs. The same effect suppresses persistent currents in sufficiently long perimeter nanorings. But local properties measured by tunneling phenomena show some superconducting properties like energy gap, broadened density of states, and finite Josephson current. Thank you for your attention. That's it.